handed it in. If already sent me the email with your file, that's great. You don't have to do anything else, but everybody should get it in by midnight tonight. I must receive it, the email, by midnight tonight. Next week's homework assignment is posted on Blackboard. Okay. Yeah. Any questions? Okay, let's go to the math then. I'm going to share my screen. And there. Okay. So we talked about the velocity of a function, the slope of the tangent lines of a function, slopes of the tangent lines. And it turned out that the velocity and the formula for finding the slope of tangent lines is the same. So we defined for a function f defined in an open interval containing the number a, the derivative f prime. Okay, so given a function, f prime is another function, the function derived from f, hence the name. So f prime is related to f. It's not generally equal to f. And 2 people entered the waiting room. Okay, this is why I need to figure this out with the. Okay. Okay. Oops. Nope. 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 I can't do it that way. All right. I have to share this screen. Or else you won't see anything. Okay. Now. Oops. Okay. Okay, yeah, so this is the definition we had yesterday. F prime at the number a is defined to be the limit as x approaches a of f of x minus f of a over x minus a. And well, one of the things we noted yesterday is that this expression is a slope of a secant line. Okay. Which is why this limit gives you the slope of the tangent line. It's lots of other things. It's giving you a change. Okay, f prime doesn't always exist. We're going to look at an example in a minute where it doesn't exist at a point. But first of all, I wanted to give you an equivalent definition to this one. Okay, this definition is really important. All right. If f is defined in an open interval containing a, then it's also the case that f prime of a is the limit as h approaches 0 of a plus h minus f of a all over h. Now let me show you why that's equivalent. Okay, so we have with the other definition, if x, we can write, okay, x as a plus some number, all right? So in other words, x minus a is equal to h. And if you're thinking about x approaching a, that means x is close to a. And if you could see my fingers, I made air quotes. Okay. X is close to a. So this number h is small. You're thinking of this h as being small. Although it doesn't. Oops, that changed. Nope. Okay. So you're thinking this h is small. It can be small negative or small positive. But okay, I can write x close to a but not equal to it as a plus some non-zero number. All right, then if that's the case, f of x, f of x minus f of a over x minus a, can rewrite in terms of h, is f of a plus h minus f of a. And x minus a is just h. Okay, so saying that x approaches a is the same as saying that h, that number h, or the numbers h, because when x changes, so does h. It's the same thing as saying that the h's have to go to 0. Okay, so that's why these definitions are equivalent. The limit as x approaches a of f of x minus f of a over x minus a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. And you can use either definition. Some people like one over the other. Any questions about that now?
No,
I
ma'am.
usually, okay, good, thank you. If I were in a normal classroom, okay, looking out at your faces, at this point, someone always asks, I know an easier way to do it, find the derivative. Can I use that? The answer is no, not yet. And actually, they usually mean they know how to differentiate polynomials. We're going to learn a whole lot more than just differentiating polynomials. We are going to get some easier ways of computing derivatives, because taking this limit every single time you come across a function is, well, it's tedious. Okay, so you need some shortcuts at some point, but not yet. Right now, I want for you to use this limit definition. I want you to get a feel for it, because this is the definition. It doesn't just work for polynomials or trig functions or logs and exponentials or combinations of these things. It works, period, for any function out there if it's got a derivative. So this is what it means to talk about f prime of a. It's a limit. Okay, let's take a function. And I hope I left enough room. Let's sketch f of x as the absolute value of x. Okay. That looks like this, right? Because by definition, absolute value of x is x if x is greater than or equal to 0, and it's minus x if x is less than 0. Okay. So the absolute value function has domain all the reals. And in fact, this function f is continuous. At each real number. So it's a nice continuous function. But, okay, it's straight line here, straight line there. And you've got this corner at 0, 0. Corners are bad news for derivatives, okay? Let's compute the derivative for this function. Okay, so f prime, I'm going to use the new definition, f prime of a. Okay, I'm going to use this one. The limit is h goes to 0 of f of 0 plus h minus f of 0 over h. And okay, let's see. I'm going to have to split it up, I think, into two cases. So let's just, okay, I'm going to be computing this. But let's look separately at this expression. No, I want this. Okay. This expression inside the limit. So f of 0 plus h minus f of 0 over h. Well, that's the same thing as f of h minus f of 0 over h. And f of 0, absolute value 0, 0, and the absolute value of h is h. Okay. So this limit then becomes all right. But let's look at this function. We're looking at limit as h goes to 0 of absolute value of h over h. Well, let's see. For one thing, you can't put 0 in for h, right? But the absolute value of h over h, a real number that's not equal to 0 is, oops, how did I do that? Is, okay, it's h over h if h is greater than 0, and it's minus h over h if h is less than 0. Okay, well, h over h is 1, and minus h over h is minus 1. So let's graph this function. We may have done this before. H is not defined, the function is not defined when h is equal to 0, but it is defined every place else. And let's see, maybe I'll put the graph in red. So you get 1 for h greater than 0, and then there's a hole down here too. and minus 1 when h is less than 0. So there's the graph of the absolute value of h over h. Is that function continuous at 0? Let me put 0 on there.
No.
No. You've got to jump there at 0. This is not, in fact, it's not continuous. It's not even defined. So it can't be continuous. But the limit as h approaches 0 from the right is going to be the limit as h approaches 0 of h over h, because when h is greater than 0, absolute value of h is equal to h. That limit's 1. The limit from the right is 1. The limit from the left, well, you can see it on the graph. It's going to be minus 1. Let's write it all out, though. That's h2. Okay, well, absolute value of h when h is less than 0 is minus h. Okay. So the limit from the left and the limit from the right are not equal. This one's equal to 1. And the other one is equal to minus 1. And that means no limit, right? The 3 dots mean therefore. And the limit as h approaches 0 of the absolute value of h over h does not exist. So f prime of 0 does not exist. There is no derivative at 0. Well, I'm out of room. If h is positive, no. Let's see. But tell me this, suppose a is a positive number. And stop that. Okay, well now, if, yeah, and let me correct that. I put in 0 for h. So I should call that 0. Yeah, the only place where you have a problem is at 0. If a is positive, f prime of a would be the limit as, okay, I'm doing the h definition. The limit as h goes to 0 of f of a plus h minus f of a over h. And that would be the limit as h approaches 0. Well, a is positive, so if I take h small enough, a plus h is positive, and that means that the absolute value of okay, minus the absolute value of a over h. Totally out of room. Let me go up here. This would be equal to the limit as h approaches 0. I always think I've left plenty of room and then I didn't. Okay. Okay. So the absolute value for positive numbers would be a plus h minus a over h. And that's the limit. Okay. A minus a zero of h over h, and that's just 1. So as long as, yeah, f prime of 0 does not exist for that function. If a is not 0 and it's positive, f prime of a is 1. If a is less than 0, f prime of a is minus 1. And in fact, I computed the limit, but you can just read it off the graph here. If I take an a over here, now this is actually a picture of f prime, I'll call it, yeah, f prime of a, okay. If a is positive, f prime of a is 1. If a is a negative number, f prime of a is minus 1. Only place you have a problem is at 0. But yeah, so some continuous functions fail to have derivatives at some places. Actually, okay, for us, that won't, these places won't be that numerous. Okay, so, and a dead giveaway is if you have a corner like this, or if you have a cusp, something of graph that looks like that, yeah, that you're not going to have a derivative where you have a corner or a cusp. There are actually continuous functions that don't have a derivative anywhere. That was kind of a surprise to mathematicians when they figured it out. But that's a little beyond us. So our functions are a little simpler. Okay, any questions?
Not right now.
Okay. Okay, let's do some more examples. Yeah, your next week's homework, like the first set of problems is find the derivative using only the definition. Okay, so we did some examples yesterday. I'm going to do some somewhat more complicated ones today. And your test, oh, somebody entered the waiting room. Okay, let me go back. This is a very good stopping place momentarily. Okay, is that everybody? Okay. Go back to the screen. Okay. Please let me know if you can't see my screen. That's kind of crucial. All right. So we want to find the derivative for this function, and it's going to be a little bit tedious. That's a cubic polynomial. Okay, would you rather use the x approaches a definition or the h approaches 0 definition? Pick one. Somebody? Nobody's willing to, okay. Nobody's willing to
I'm
pick
sorry,
one?
I'm trying to run the calculations in my head.
Oh, that's, okay. All right, well, I'm gonna use the H definition since we used the A one yesterday. And in fact, the next problem, we'll go back to X approaches A. You can use either one, okay? You might find one easier than the other, but they both work. Okay, so let's write down what I'm finding first. F prime, well, if it's F prime of X, then I'm using the H definition. The H is the second letter. So yeah, the H is what's changing. Then this is F of X plus H minus F of X over H. Yeah, I say X is changing. For the moment, X is fixed. And in the limit, it's the H that's changing, not the X. Okay, so let's put in our function. Oh, X plus H. That means all the X's get replaced by X plus H. That's F of X plus H. Whoops. And then F of X is just okay, X cubed plus X plus 1. Okay, that looks a little daunting. I'm going to expand that X plus H cubed. So maybe, okay, if you know the binomial formula, it's really easy. But if you don't, you can always just multiply out. Which is, okay, so X plus H squared is X squared plus 2XH plus H squared. Whoops, not that way. Okay, times X plus H is equal to X cubed plus 2X squared H plus XH squared plus X squared H plus 2XH squared plus H cubed. And that's putting all that together. Let's see, you got X cubed and H cubed, but I've got an X squared H there and an X squared H there. So that's 3X squared H. And then I've also got XH squared there and XH squared there. So that's 3 of those. And then I've got H cubed. Okay, so kind of did that separately. But okay, now the limit then is a limit as H approaches 0 of X cubed plus it's not writing. Oh, there it is. Okay. X cubed plus 3. Every now and then it does this. What in the world? Oh, no. Okay, maybe it's that. X cubed plus just a minute. Okay. Let me just what can I do? It just bugged out on me. Okay. Okay. Let's see if that fixes it. It's a little freaky to have my technology going out when no technology, no class. Okay, so that's x plus h cubed. Oh, this is a little bit long. Plus x plus h plus 1, and then, okay, taking that minus 3, we've got minus x cubed minus x minus 1. That's the entire numerator. Okay, but I can clean some stuff out here. I've got an x cubed there, and I've got minus x cubed there. Okay, so that adds out. I've got an x there and minus x there. And I've got 1 there and minus 1 there. So I can simplify this. This becomes 3x squared h plus 3x h squared plus h cubed. And there's still an h left over there. Okay. Yeah, every term that didn't have an h in it added out. And let's make sure I didn't forget anything here. Yeah, I got that h there. Okay. All right, so at least that has fewer terms in the numerator. But now, since every term in the numerator has an h in it, I can factor an h out of the numerator. And this is looking good because now I've got h as a factor on the top and h as a factor on the bottom.
Couldn't there be a h
Yeah.
with the 3x?
Yes, thank you. I just saw that myself. Thank you. Yeah, please point out things like that. Okay, yes. Let's see if I can do a better job of putting that back in. Okay. Yeah, there is an H there. So I took out 1. Okay, there's 1 left. All right, so now I can cancel out those H's. And my 0 over 0 problem's gone. So we have 3x squared plus 3xh plus h squared plus 1. And as h goes to 0, okay, let's see. This is going to go to 0 because it's got an h in it. That's certainly going to go to 0. So we wind up with just 3x squared plus 1. Okay, that's equal to f prime of x. Any questions? And I left enough room for that one, surprisingly. Okay, so what did I do? Well, you do what you can do, okay? Your choice of what to do depends on your problem. In this case, we had a polynomial that we could expand, and that worked fine because after expanding, we could, well, the x terms, the x only terms all added out. What was left, each factor contained an h. That meant we could factor an h out of the numerator. We could factor an h out of the numerator, then we can cancel an h out. Now your 0 over 0 problem's gone, and you can evaluate the limit by direct substitution. Okay. Any questions? Okay. All right, I'll take that as a no. Let's do another one. And how are we doing on time? Oh, 8:37. We're fine. Ooh, I left enough room for that one. Okay.
Well, ma'am, I remember somebody tried to ask an earlier, what's the difference between using the x or the limit as x approaches a and the limit as h approaches 0?
There really is no difference. Well, okay. I'll work that problem out using the other definition. How about that? We'll see if we get the same thing. Oh, okay. What you do in between is a little bit different. Okay, so let's do it using the other definition. May even have enough room. Where did it go? Here we go. Nope, nope, nope. Don't want that. All right, so f prime of a, this time I need 2 letters. All right, and I'm going to let x be the thing changing in the limit, so that means I've got to call whatever this is something else. Okay, and it was this definition. And f of x is x cubed plus x plus 1, and then minus a cubed plus a plus 1 over x minus a. Okay. It's important to keep the same function, but I believe that's right. Okay. So this is now equal to the limit as x approaches a. Well, I'm going to group terms. I'm going to group those 2 cubic terms together. So that takes care of that and that. And then I'm going to group the x terms, well, just x to the first power, okay, the x and the a. There's an x and then minus a, right? Because you got x there, and that's really minus a because of that minus. And then you have, okay, and we've also got 1, and that's really minus 1 because of that minus. So that's it. Okay, the numerator simplifies to x cubed minus a cubed over plus x minus a, and that's all over x minus a. Well, if you have something of the form x cubed minus a cubed, x minus a is a factor. Let me show you why. I'm going to divide x minus a into x cubed, and then put minus a cubed out there because I'm going to get some things. Okay. 0 ax squared plus don't know if I'll need all these. Don't know if I'll need them. Okay, so I'll put them in. Make that over there. Okay. How many times does x go into x cubed? Well, it goes in there x squared times. So x squared times x minus a is x cubed minus ax squared. This is just like when you divide numbers. Okay, same algorithm. Now subtract x cubed minus x cubed is 0. And 0 minus ax squared is plus ax squared. Okay, now how many times does x go into ax squared? Ax times. ax times x minus a is ax squared, and I need 0a squared x. Okay, a times x minus a, ax squared minus a squared x. So I'm going to bring down that 0a squared x. And again, okay, that changed. Subtract. And okay, if you've done it right, this part goes away. But this was minus minus, so it's going to be plus a squared x. Come in, just a minute. My ladies are here. Good morning. Good morning. I'm teaching my class. Okay. Yeah. All right. Okay. So then x minus a then goes into a squared x, a squared times, okay, and a squared times x minus a is a squared x minus a cubed. And okay, we have the minus a cubed brought down from above. That's 0. So you can, if you have something of the form a cubed minus b cubed, you can always factor an a minus b out of it. Okay, if you, I don't know, I hope you've seen this little procedure before. But okay, this changes our problem. Now I can factor, I write x cubed minus a cubed in factored form. So the limit as x approaches a of x cubed minus a cubed minus x minus a over x minus a is equal to the limit as x approaches a, okay, of x minus a times, okay, x squared plus ax plus a squared. I have an x minus a out there. But now look what's happened. I've got x minus a there and x minus a there. So I can factor x minus a out of the numerator. And I have x squared plus ax plus a squared. And then this part gives me minus 1. And it's all over x minus a. Okay. Well, by doing that, now I've got x minus a as a factor on the top and x minus a as a factor on the bottom. I can cancel. And once I cancel, the 0 over 0 problem has gone away. And I have, wait a minute, something's not right. Oh, yes, it is. It's fine. Oh, it's minus 1. Taryn Hill. Oh, she's in my next class. Okay. Uh-oh, maybe I made a mistake here. Let's see. Well, the limit, I don't think that minus 1's something's wrong there. Okay, but when I put a in now with direct substitution, I've got a squared plus a squared plus a squared, which is 3a squared minus 1. So I made an error somewhere. It's supposed to be 3x squared plus 1. What did I do wrong? Oh, I see what I did wrong. That plus, that plus there. sort of magically changed to a minus. That's supposed to be a plus one, plus, not a minus. Okay, so that's what's wrong. Okay, that's a plus. That's a plus. Yeah, because you're supposed to get the same answer regardless. But we do. Okay, so f prime of a then is 3a squared plus 1, which is the same thing as saying that I let a equal to x, 3x squared plus 1. Okay, so you get the same thing either way. Okay? Yeah, the algebra you have to do in between can be different if you use one definition or the other, so that you can, well, use the one that makes your work the easiest. I hope that answers the question. We did it both ways. Let's see, what time is it? 8:47. Oops, no. Okay. I don't know if I'll have time to get through this one, but I'm gonna start it. I don't want to do it both ways. Okay, I'll just do the x approaches a definition for this, okay? So I want f prime of a, the limit as x approaches a of f of x minus f of a over x minus a is equal to the limit as x approaches a of 2x plus 1 over x plus 3 minus 2a plus 1 over a plus 3 over x minus a. Okay, this is a fraction. The function is a fraction. It's a rational function. And looks like I need a common denominator in the numerator. We did a fraction yesterday, but it was a simpler fraction. Okay, then this one's going to be a little messier. Okay, but let's keep going here. This is the limit as h approaches 0. Okay, so the common denominator is going to be x plus 3 times a plus 3. Still got that big bar there. And the numerator, okay, using, let's see, a over b plus c over d is equal to AD plus BC over BD. And I also just like to check myself. Yeah. Okay. So let's see if we can simplify all that. Oops. Okay. Got to stay with my x approaches a. You can't mix them up. Okay, so grit your teeth and multiply out. Well, one thing, okay, this complex fraction, I can simplify that. Oops. Okay, using that. So actually in the denominator, I'm just going to have x plus 3 times a plus 3 times x minus a. Okay, so what's the numerator? 2xa plus a, okay, plus, okay, multiply by 3, 6x plus 3. So that gets this multiplied out. And then minus, okay, it's going to be 2ax plus x plus 6a plus 3. Okay, let's go. That's multiplying this out. Okay, let me check. 2ax plus x plus 6a plus 3. Okay. Okay, so, but now some things are going to add out in the numerator. Let's see. I see this and I see minus that. And there's a 3 and a minus 3 because there's a minus there. Okay. Outside the parentheses. Doesn't, let's see, I don't see anything else that adds out. But okay. Let's simplify. Let's get rid of those. Okay, so the 2xa adds out. But we have, oops, we have a plus 6x, the 3 added out. Okay, so I have to write that. So, and then, okay, so yeah, so all I have left is from this first expression is this and this. That added out. I've got minus x from right there. And I've got minus 6a from that second part. Okay, so that's all we've got left in the numerator. Oops. And okay, well, let's see, I could go two ways here. Oops, oops. Well, why don't we combine the x's and the a's? Combine the a's and the x's, okay. I've got a minus 6a is minus 5a. And 6x minus x is plus 5x. And now I'm going to factor 5 out of the numerator. So that's going to leave me, funny looking 5. Okay, that's going to give me 5 times x minus a. And I've got over x plus 3 times a plus 3 times x minus a. Okay, well, I've got an x plus a, x minus a rather, an x minus a on the top and an x minus a on the bottom as factors. So I can cancel them out. And now, okay, well, once I do that, the 0 over 0 problem has gone away. That's what you're going to be doing every time. It's getting rid of the 0 over 0 problem. Okay, now I can just use direct substitution and replace x with a. So this is 5 over a plus 3 times a plus 3 is 5 over a plus 3 squared. Okay. So the derivative, assuming I made no errors, is f prime of a is 5 over a plus 3 squared. Any questions? We're getting, oh, we are out of time. Okay. So let me go back to Zoom. Yeah, we're out of time, so you can leave now if you want.
Okay.
If you want to stick around and answer.
Bye-bye.
Bye.
I
If you want to stick
ain't
around
gotta
and
head up
answer.
till tomorrow, so.
Pardon?
I gotta head up to Lamar and get something I need for another class. So I'm gonna scram. Have a good day, Miss Kennedy.
You too. Mr. Franco, you can access the recordings on Blackboard, okay? Every day I post, and also Mr. Flores's recordings. There's a link posted on Blackboard, and yeah, I get a thing from Zoom every day and I post it according to the date. And the video's not there, but a link to it is. Okay. That's my other class. Okay. Okay, so I hope that answered your question. I'll try. Okay. It said the recording was